get back to our picture, right? So far we have not left this picture yet, right? I mean, it's this lecture, right? The two application we talk about, right? The few exact application we talk about. We try to learn F data. We have lots of samples, images. We try to learn representations. We do this end-to-end, open loop, right? Do some weird constructive learning, right? Some objects, some engineer try not to collapse, make them span, make them, similar things. Or we do a little bit of auto-encoding, or use this, right? Or if we have labels, you have classifiers, if we have labels, right? We can use the class label to guide us to learn those features, right? Optimize, create, so that the feature will be different classes will be spanned, and similar class become linear. Okay, we can use the classification. Actually, the class labels is additional information, allows you to learn those representation better, easier. That's it, right? So you guys should become much better now, right? All the people who ever talk about the supervised learning, unsupervised learning, self-supervised learning, weakly supervised learning, they're just the stupid terms people come up with, make them as if they're working on different problems, right? They're all different variants of the same thing, as if only that how much you know a little bit more about the distribution of the data X, how much information I gave you. Those have the same class. I gave you that additional information. If I didn't give it to you, go figure it out, right? They're still similar. Cats still looks like cats, okay? I've labeled them as a cat, just make your life slightly better, okay? That does not change the fact. Those two images are still cats. Understand? Understood? The information is still there. Just gets a little bit harder for you to get that information out, right? Or I segment it out, right? Making your life even better, right? Not only tells you there's a cat in that image, it also tells you which region the cat is, okay? Pay attention to that part. Make your job slightly even more easier, give you a little bit more information. See, the whole world is about we're playing the game of information game, right? So if I don't give you that information, you just gain from the data itself, okay? The distribution already has all the information there. Especially you only want to know about the distribution. The information is already in the data. Now, so we do this. You can do this open loop, make your job a little bit harder, but still may converge. If you have enough engineering, if you use the right heuristics, you have billions of images, right? You can probably still train a decent F, like Dino did. But if you know a little bit better, you know the object function, you know the architecture of F, your job is much easier. Or you can use autoencoding, right? Do a learn decoder. Use ML, right? To enforce the encoding is learning something low dimensional, right? So that you can recover the original data from very small fraction of the observation. Enforce that this encoder decoder has learned the low dimensional structure correctly so that even a fraction of the observation contains sufficient information to recover the sample. Okay? Remember? That's actually the test. Right? So that to avoid, you learn a trivial identity map. Right? Just like when you do the open loop, to avoid, you learn a trivial invariant representation. Everybody can collapse to a single point. Right? It's very similar ideas. So, and you can do this, right? Or the lecture 9, right? We also talk about, you can also do this, you don't care about this. If it's harder for you to measure things, the image we still can measure, right? Still have the image, we can do the compare the pixel patches and so on. But for 3D, it's harder, right? So I don't have the ground truth. So we do the closed loop. Right? We talk about that. In theory, it's possible. Even if I can regulate my feature point, as long as the distribution is low dimensional, I actually can do the closed loop transcription, right? I'm also allowed to do that. I can do that. Now, what's the remaining question? Suppose I have learned such a autoencoding. Suppose I have learned this very, very well, right? How do I get here? How do I know what are those dots, green, blue, where are they in this space? Now you know. Suppose you are perfect. Okay, you have learned, you have make something linear, nonlinear to linear. Okay, you have learned make those manifolds to be linear subspaces in this space. But where are the subspaces? In order for me to generate the apple, right? For example, this is the apple. I still have to sample from that line, right? That subspace, then decode it back to get an apple image, right? How do I access that? Then I have to find those subspace one by one, sure. Even there's only one subspace, I still have to find, even there's only one. For example, the green one, I still have to find that one, right? What is the basis? U1, U2, U3 that span this red subspace, right? How do you do it? Run the PCA. Because you have enough Z's, right? Z1, Z2, Z3, you have a lot of Z's there. Stack them in the matrix, do SVD. But if you have a lot of data, that's very expensive. What do? You do power iteration. You start with a random vector. You do contraction, right? You converge to that direction. You get a V1. You get a U2, and so on and so forth, right? That's exactly the denoising process, right? Hence, that which suggests if I want to get a hold of those subspace, what do? I have to build a bridge. How do I access those individual subspaces? How do I access those features? If it's a PCA, it's easy. I learn U. The network, the operator is probably a few iterations, right? If it's multiple subspace, if they are orthogonal, we also learn how to do it, right? That's lecture 3 or 4, right? Because if those subspaces are orthogonal, dictionary learning, right? Exactly, we learn a dictionary. We learn rotation so that I make sure those subspaces align with my coordinates, x1, x2, x3, right? Then I know x1 representing apple, x3 representing orange. Remember, this is about accessibility. How do I identify those subspaces? Now, in general, of course, it's more general, right? We don't have the single subspace. We do not necessarily have those subspaces are perfectly orthogonal to each other. What do? We treat it as a general low-dimensional subspace, low-dimensional distribution. We can access through denoising, right? Remember, PCA is denoising. It's just a special case of denoising, okay? Then we just access them through a very generic denoising process. Diffusion denoising process. Start with anything random, gradually converge to those subspaces, right? Except those are, unlike this case, is very general, right? Some curve. In this case, maybe they're better, right? I can still do this. Conceptually, exactly doing this, okay? Right. Now the question is, there's a slightly different, right? Where we know we're doing denoising. We know we're from some random converge to those low-dimensional structure. But now, unlike what we learned in your chapter 3, which we're trying to diffuse or denoise onto a general distribution, low-dimensional distribution. Here, this distribution are piecewise linear. They're simpler. They're more structured, right? Hence, now I can hope more, right? I can wish a little bit more. Maybe those denoisers are simpler. Second, maybe those denoisers are more efficient. Okay, that we can hope for. 对不对？就跟 PCA 一样， right? If I'm running PCA, I have power iteration. Far more efficient than any gradient descent. Okay? 对不对？ So maybe we can hope those a little bit hopeful, right? See if they can help me. If the structured distribution, they are a mixture of Gaussian or mixture of subspaces, does give me more. Yes, it does, right? So this is what the people are, again, in the beginning, they don't know what they want, right? I mean, there's kind of so learning those, learning this general distribution is kind of hard, especially image space. It's very high dimensional, right? and the pixel space, millions of dimensions, right? It's very hard. I mean, then also maybe we can make if we can make what's in the transform the data into some feature space. If the feature space is kind of regularized, it's kind of better behaved, maybe the diffusion is easier to learn. Okay, that's the justification. That's exactly what they did. Okay, so well, let's use some autoencoder to. This is the image, right? It's very hard to learn distribution here. Let's just compress into Z. Learn a decoder, encoder, decoder. Convert X into some space. Again, they don't quite know what Z they want. Well, how do we make the Z looks like a Gaussian, also a little bit of factorizable, right? So that the Z behaves, the distribution of Z behaves like some shape, right? This is exactly the idea of VAE. Say we want to map X to Z. Z, the distribution of Z fits some distribution. Overall, like a Gaussian, also somehow factorizable. The posterior has certain form, factorizable form. In fact, VAE, the object function they chose, are precisely is in the book, right? You can take a look. Actually, till this day, I don't know what that prior is really promoting. But roughly is promoting sparsity and isotropicness. Okay, that's it. So they're playing with similar heuristic, just make the Z have the shape is a little bit better. Okay, that's it. Then in the Z space, also the Z reduced the dimension a little bit, right? The dimension was reduced quite a bit, right? They're kind of doing this kind of mask autoencoding cap. Make sure the learned distribution is highly compressive. They're sort of already using the fact that the intrinsic dimension of X is kind of low, right? They manually force the dimension to reduce, okay? Using the UNet, right? Kind of structure. Really reduce the dimension to a very low dimensional space. Enforce the dimension to be low, right? And also make sure Z, the distribution kind of, uniform, right? Then they try to learn a diffusion map in the space of Z. It's called the latent diffusion, right? To use the UNet to emulate in this kind of diffusion map. Right? So they train this. Right? This is the 2020 CVPR paper. Right after this, someone invested about $50 million, right? 训练了一个 diffuser model 叫做 stability AI， 对不对？花了$5000,000啊 ，to engineer this so that then majority and all the people are doing this now, right? To generating images, so on. And it works. But a lot of engineering goes in there, right? Also, you don't quite know what the VA is doing. It's enforcing some no dimensionality. So heuristic is still kind of doing the right thing. You enforce leveraging the distribution of X should be low dimensional. And in the feature space, the distribution kind of regulated in somehow, in a very soft way. Okay? You want the hence in the latent space, the diffuser, the denoiser is relatively easier to learn. Okay? With some here they use UNet to do this. Although why, I don't know. Well, they tried. It works somehow, right? What is the form? They tried, okay? Somehow works. After 对吧？烧了$5000,000 somehow has still works, right? And then in the space, in the latent space, yes, you can sample. You can actually build. This is standard book stuff. 这是我们现在是 standard book stuff, right? 你们应该这些东西应该你们其实完全是就像 homework 一样了啊。对。Right, for you guys, once you have in the latent space, you know there's a distribution, how to build a denoiser, right? All kinds of different discretization, right? About right? Variance exploding, expanding, or variance invariant, flow matching, choosing different weights. It's up to you, okay? Try which one works better for practical data. It's up to you, okay? As long as it doesn't blow up, okay? As long as it's kind of stable, right? As long as you can afford it, right? Try different things. Right? Make it efficient, and somehow this is a stability AI, right? You can actually generating different type of images. That's what the people have been playing, right? All right, good. Get it? 所以你看很多的 practice. I'm not saying they're wrong, right? They're no. Actually, they are using the right heuristics, right? There's actually a lot of very careful thought going into it, but it's not rigorous. It's not clear. Okay, it's not fully explained, right? And it gets embedded in all the heuristics, right? A lot of entangle there. Right? The practice, right? Even somehow people, right? They still don't know what the heck they learned here. What is the structure here, right? The control using some clip to do is still cross attention. Somehow yet generating relative image, but the control is not perfect. It's actually far from perfect. Okay. Then they spend another last 5 years doing what? Control net, right? And try to control this sampling better. OK， 所以就是做了很多亡羊补牢的事儿。为什么？就是第一个羊圈没修好，对不对？套路漏洞太多，所以后来又开始又发几百篇文章去 fix。OK，you write a lot of papers to fix this thing, right? That's it. And also, this thing is extremely slow to train, right? Those thing takes 几十万个 epoch to train. 几万 if not 几十万 right? Takes weeks, months to train to get it, to improve, to converge, right? Very expensive to go through those things. Very painful, but still people practice, right? But this is the example, right? People, again, later on, people actually start. This is the slides I borrowed from Xie Sanling, right? See, the different, if you have a different representation, if you learn different autoencoding, right? People in the past, after this, people try to improve it using different, get a better autoencoding, get a better Latin representation, right? You learn different representation. People see improvements, right? You use, this is the original one, REPA, DDT, anyway, to see that if you get a better representation, right, the performance at FID actually improve. And also training gets faster. You see that trend. This is flops. How many training? The training gets converged faster. The performance improves faster. So better if you get a better representation. The diffusion model converge on those representation distribution is faster. And also the quality gets better. 明白吗？所以这是过去这么多年在瞎折腾，对不对？大家就开始折腾，对吧？把这个 representation get better, get a little bit better, get the faster and so on and so forth. They are trying basically improving this part, right? If you get this part better, this part gets easier, right? But still, they're using UNet and still. So people, because they don't know what it is, they don't dare to change anything. Okay. Whatever have worked before, they only do minor tuning. All right. Let's get this a little bit right. It's to be stuck with UNet for a long time. All right. Can we do better? So we know we have solved this problem. Suppose we have learned, right? We have learned very good mapping X to Z. And if our representation has made Z highly well structured, piecewise linear, right? Incoherent, so on. If we have learned such a Z. For example, Dino has that tendency, right? Really try to shape the feature space to be piecewise linear and expand and so on. Now, we wanted to access the Z, the distribution of Z, right? We want to sample it and to decode it, right? That's our problem. So hence, we're no longer take this darn thing, do a heuristic autoencoding to a feature that we don't quite know what it is, okay? Maybe dimension gets reduced a little bit. Overall distribution looks like a Gaussian, but what's internally, we don't know. Right? Internally, it's still very entangled, still nonlinear and so on. But if our feature mapping already learned Z to be highly structured, already linear and incoherent, then maybe building the diffusion, denoising becomes easy, quick, right? We have this problem to deal with. This is what Xie Sanling did, right? This is exactly what they did, right? 但不要忘了，on the team there's a Peter Tong, right? He was my former student, right? He's the one actually did the closed loop transformation, right? So the people, if you know the mental picture, you are not afraid of high-dimensional feature spaces. The reason the original do VAE, right, they reduced to low-dimensional because they don't have other ways to deal with compression. They cannot deal with this implicitly, right, through the denoiser, through structured denoising, right? They have to do this in a very manual way, in a very brute force way, using UNet to reduce the dimension to low dimensions. And in fact, the feature gets entangled together. Hence, the diffusion, it's very hard to learn those internal structures, right? Take many, many steps. According to Xie Shanlin, this actually used to take like, hundreds of thousands of steps, epoch, to train. But now, if you have learned a very good encoder, if your encoder is already from linear, basically here is already piecewise linear. Even the dimension is very high. For example, 700多位，对吧？这是4维，这个叠到每一个 channel 啊，到4维。There's many channels, of course, but there's actually 每一个 channel is like 768位。It's very high dimensional space. So I embed this Dino, right? Embed those features in a very high dimensional space. But their intrinsic structure is very low dimensional. Okay. There's some PCAs in there, right? We're not afraid because we know how to access those things. Right. Hence, for those, how do we converge to linear? If this is already linear, we know what those denoiser looks like, right? If we're denoise or the denoiser for those piecewise linear structure, they're exactly like create, like transformer. So now there's something very interesting, guys. Right? In the beginning, when we do the autoencoding, why those architecture are like structured denoiser against the piecewise linear Gaussian? Why? Because we want them to. We want this become piecewise linear. That's our goal. That's our objective. Hence, those architecture are exactly reflect the fact from the objective of the delta R. Okay? Now, in this case, why the operator looks like a denoiser for piecewise Gaussian? Because the distribution looks like that. It's not the Golang, it's actually the structure of the feature has this structure. Hence, the denoiser naturally has to be denoised against piecewise Gaussian. Get it? So there's a very interesting thing, right? This is by design. This is necessary. Okay? Turns out that they're all the same type. They're all denoiser against mixture of Gaussian, mixture of subspace type. Get it? 所以同样的 architecture actually works for both cases. And that's exactly what I think Xie and Linda did, right? That they just used the transformer to do the denoising, to approximate this, this operator, diffusion model. Right? But Xie actually tried, right? He remember before this he did the Sora is using diffusion DIT, but it's applied on this feature. It's very slow. Yeah. He said actually doesn't work that well. It takes hundreds of thousands of iterations to converge. Right. But in this space, the same diffusion transformer right takes a few hundred. In fact, takes 40 epoch, already better than DIT before. All the other previous method before. 这些可是要花上对吧？几万次啊，几十万次迭代，现在就几十次，就已经比原来好了。 feel like PCA, right? Because the structure you're pursuing is very, very linear, very simple. Even you are pursuing those structure at a much higher dimensional space, but the structure of the distribution, you benefit tremendously from that, right? So this is, if you do this, you can see that right now, only the performance actually become much better. Right? You can also try different encoding, by the way. The Dino seems to work. Remember, you can also try MAE, right? But the Dino seems to work best, right? You can use, remember the first part, right? 这个你可以试不同的东西，对不对？这个 part 可以试不同的MAE 啊，什么乱七八糟的，反正这个，you can use the Z, you can use the diffusion to try different the feature learned from different auto encoding. Turns out that so far Dino is still the best, right? You can get a different classification and also that you can see, right? What it has said, right? They actually, in the beginning, they're actually kind of afraid of, this is actually the loss, training loss, if the dimension of the channels, right? Remember, the Dino is a 768, very high dimension. In the beginning, they're actually quite afraid of this. This is much, much higher than the VAE. VAE is only 4, right? So they actually started with reducing the dimension to something low. Actually, turns out it doesn't work that well, right? Turns out they actually let the dimension gets really high. So this is something very interesting, right? You give the feature enough space, as long as in the high dimension space, the structure is linear, it's highly well behaved. Pursuing them, converging to them is much faster than you actually squash them together. 就跟你在手上解了个线团，对不对？一团线在一个平面上，你把它弄不清楚怎么弄，拉起来抖一抖In the higher dimensional spaces, maybe things are much easier, right? To find those low dimensional structures and make them linear, make them smooth, and you have a much easier way to converge to them, right? Find them very quickly, right? So diffusion successfully overfit and get very, very perfect examples, right? So this is actually give you an idea. See, if you have the right structure, mental picture, you won't be afraid of high dimensional spaces. Right? You're only afraid of high dimensions because you didn't do it very well, right? You don't know what you're doing, right? As you can see, that this actually converges not only in the higher dimension space, that it actually converges much, much faster, right? Even much better quality. This is actually quality, FID quality, right? Significantly across the previous DIT, the previous REPA. Those are even the methods even before DIT, okay? Before the stability AI, right? This is also Sora and so on. Those are already, she said in his previous work, he's tweaking all the other method, right? To get a better performance, this REPA and so on. This is already after his work on Sora and so on, and DIT and so on, right? But with Dino, with the higher dimensional feature space, it's actually converge much faster and also much, much better performance, right? And you can see that this is some of the reports. Yeah, you're happy to try, but yeah. And another thing is interesting, right? In fact, there's something very, very interesting with this encoder decoder learn, right? If you say generating parrots, right? Right? The image is very diverse. Unlike a previous DIT, a previous stability AI, it gave you all the birds very much a big headshot. Okay, the body actually quite uniform. 明白吗？为什么？你想一想。Because the DIT, it learned those things from different angle, different cropping, different scale. Okay, very diverse. It has some semantic picture, right? The Dino actually learns something very, very semantic. Group all the possible images together. It learns much, much more images. So it really grouped a lot of different things that have a similar features. Hence, the decoding can actually generate very, very diverse, even around the same neighborhood. It actually can generate much more diverse images than before. Remember, this is what you want. You do want to, for example, hamburger, right? You want to have one, all the different ones. But if you look at the previous image generator, they generate very, very, not the diversity is much, much lower than this. It's quite interesting, right? What else can you think about doing, guys? If our guess mental picture is right, the Dino gives very high, but the intrinsic low piecewise linear dimension, right? Has this picture. The Dino feature are similar. By the way, Dino is not even the best. Okay, we already know we can do better, right? Even Dino is very heuristic. We just talked about it before, right? But indeed, suppose you can get a very high dimensional feature, highly linear, piecewise linear. What can you do? You can bind to text much, much better than what's inside here. Okay? Before stability AI is doing all this weird image pair and do a clip, right? You do conditioning on each layer. Those UNet try to control generating text condition the images, right? I don't know what they're doing. Okay, I don't know about you, but I honestly, till this day, I don't know what they're doing. Okay, how they do this conditional sampling through this cross attention. Okay, no, you don't, right? 所以说我就说嘛，就是亡羊补牢嘛，对不对？后来一堆什么 control net，对吧？control this, control that, right? But if you already have very good semantic features here, right? This is images really get into some highly structured. Then you combine. This is apple. This is orange. This is different. You get highly correlated things. Get very modular memories, right? You'll be able to synthesize, combine them together. Right. I can tell you this is something that she's in the Peter Tom they're working. Actually, it turns out if you get a very good, if you train very massive visual representations, you get a very good visual representations. Turns out their binding to natural image, natural language become better and better, much easier. Okay. So this open up a lot of new things, right? Playing with much structured visual representation feature space. It's much pleasant than before. Even the dimension is high, but that's the whole thing. You want to be dimension to be high. You have a lot of freedom. You can have a much bigger memory. You can remember a lot. You can have a lot of more diverse objects. Your memory can be much more rich than before, right? The capacity is bigger. 就跟我们的大脑，对不对？这么多的 capacity, so we can memorize a lot of things. We organize them in a highly structured way. We do want the dimension to be high, okay? We don't want to have a squash all our representation into a very low dimension spaces. We want the capacity to be high, but we want them organized. The intrinsic structure of the data gets identified and organized in that high dimensional spaces. Then accessing it is not the issue, right? It's very efficient. 记住这一点啊。To summarize a little bit, right? So to give you a little bit flavor, right? 所以希望这个课程的这些理论概念啊 clarify a lot of practice. Also to find the reasons behind some of the practice. They're not entirely wrong. Actually, they precisely they did something right. Okay, that's also make stability AI work in some things. They also try to leverage low dimension structure, although not quite there. Okay, but they limit themselves in the low dimension space. They don't give them enough freedom. The structure they're dealing with is not linear. The binding, conditioning are much harder, right? The convergence is much slower, right? They make themselves solve a much harder problem optimization-wise. Okay? But once you can learn better feature in a higher dimensional spaces, make the feature much more structured, then diffusion denoising is very simple. Even the architecture become transparent, right? Can be explained why certain architecture works and must work, have to work, okay? Have to work almost optimally efficiently. 明白吗？你就可以做解释了啊。Now, as I said, all roads lead to Rome, right? All the practice you can see, right? It's a fraction of what we're trying to do here. Different variants, different piece, open end, open jaw, auto-encoding, closed loop. Maybe some people are learning the auto-encoding transformation. Some people are learning diffusion, denoising. They actually all try to do this, right? And even just try to do this, right? Try to do this. There's all kinds of things, right? There's all the different approaches, right? Different heuristics, different optimization, different training set, supervised, unsupervised, the self-supervised, the weakly supervised, Now, see, to just first 3 steps, right? There's 3 things I want you to remember, right? 1, the first step from the data to the feature representation. Why we learn representation. Now you know why, okay? Why the data itself is not good enough, okay? The original distribution is not good enough. We want to learn that distribution, but we don't want to learn it as it is. 明白吗？我们不想只学到数据它本身那个分布，它本身 it's very hard to memorize, very hard to access, right? We want to transform it to feature space that are linear, incoherent, very highly structured, easy to access. Okay, so it's just deep. But how to learn it? It's up to you. Depends on setting. You can do the open loop, end-to-end, X to Z, contrastive, contractive learning, self-supervised, supervised, self-supervised. It's up to you, right? But at least Centennial seems to be okay. Auto-encoding. We can do auto-encoding. Certain setting images, we can set up the auto-encoding. Max auto-encoding is trying to do that. If you do have the freedom to measure X and X hat, okay? Yes, image patch, you can still predict. Max auto-encoding can do that. You can also enforce the learning process to exploit. Enforce the low dimensional structure. Okay, that's what the MAE is trying to do. Just like matrix completion. Also, you can do this closed loop to learn something self-consistent. If you don't have the option to measure X and X hat, okay, you can do the self-consistency. We also talked about this earlier, right? There are just different ways to do the same thing, okay, guys, to learn F to X to Z, such as Z has good structure, and also Z is kind of consistent or self-consistent, okay, that's it, 对吧？所以条条大路通罗马，大家要做的事儿是一样的，只是路径不太一样啊。Then the next thing, what do we do? Once we learn the good feature, we also want to access it. We want to sample it. Also want to decode it, right? We want to find where the heck this is. Then I can decode it to X. Generate a picture. Right? This is my memory. I want to find something random. So find where's apple, where's orange, where's my memory, so that I can predict. Now I see piece of this, right? I see part of the cup, right? Do a base inference to infer what I'm blocking, right? That's exactly, I'm accessing that part. I see part of the cup. I can do what we just talked about last week, right? Do this. And this is very fast to access. This has to be very fast to access, okay? The better structured FX is, easy for you to solve this problem. Even better, this is piecewise linear. This problem is very easy to solve. Okay? 明白吗？就在干这个事儿啊，没别的啊，非常简单啊。So, hence this is then those are the 2 steps. Now, second, what is deep networks doing, right? This one, right? To learn this mapping F or diffusion, do this step by step. And also we can even know, in this cases, right, if this is the goal, this is what we want. This is something we're pursuing. Then the architecture, the operator per layer share the same form. They're precisely doing, denoising against piecewise linear. Piecewise Gaussian, denoising. Even the form, 对吧？它们的形式都很像啊，都是一样的，明白吗？啊， And also decoder, just reverse, right? This linearize, this just 这把噪声去掉，这把噪声加回去，这个也一样啊。diffuse, denoise， 这个加噪声，这个只是这里的噪声是有结构的，是由数据决定的。This noise here, error, is determined by the structure of the data. Okay? You linearize, you remove the residual, and you add it back. Here is unstructured, 对吧？每个点 diffuse 就加高声、高斯 isotropic Gaussian, then you denoise. 明白吗？啊，所以有时候我们把这个叫做这个是 small noise， 这个是 big noise 啊，小噪声和大噪声啊，大家都在玩噪声啊。All right, that's very much about it. Hence, you can actually see why a common departure, such like a transformer or crate-like architecture, actually works. 对吧? Maybe you can make it even better. Actually, some of my students try to make it better. Right? Remember, even we derive a crate, it's kind of brute force, right? Don't say this is it. Okay, 这不是，这差远了，刚刚开始，对不对？对吧? There's a lot of ways to can improve. Many ways you can improve, right? 现在 crate has a batch 版本。What about causal? Apply to time series, right? There's a lot of things, right? We already talked about it, right? How to make it more efficient. This is because subsets. There's what about a linear system? No, 还没怎么开始呢，同学们，对不对？所以大家着什么急呀、啊，对不对？啊，还早。But at least we understand why a family of why those architectures should be similar. Because they're realizing the same kind of geometrical or statistical operation. 明白吗？啊，他在做什么样的去造，对不对？ What kind of operation they're doing? Actually, we know now. 实现形式可以变，可以更加越来越 efficient, but they're doing the same thing. Okay? They're trying to do the same thing. Then once you realize that, then just all the different applications, right, to different data, right, to the images, videos generation, 3D object and the scene, human body and hand motion, so on, right, and the text, language, GPT. Why text first? Because it's the easiest, okay? Text is the easiest. Easy both in terms of availability of the data. Second, also in terms of structure of the data. It's simple, okay? It's discrete, right? The correlation is easy, right? Data is easy, right? And dimension is low, 对不对？这个就难多了，这更难，对不对？ Human body is easy. Human body only have couple hundred degree of freedoms, right? Less than 100 degree of freedoms, 60, 70, depends on how you count, right? So human body, hands, vision, object. That's why this part is called the 大脑, okay? That's why this part is called the 小脑, okay? There's a reason for that, right? There's only a small part is dealing with this, right? Our emotion 小脑, right? This is the huge part is dedicated to visual memory, okay? Now you know, right? How much computing is that? How much we do this? 自然语言是多少？都没有名字，对不对？啊，有个小名字，就是前面的一点点啊，前页的这个小点点那个自然语言。要取名就叫 tiny 脑 ，right？ 微脑啊，这个 ，right？ We don't even have it doesn't even deserve an independent name, right? This one deserve one. This is visual, right? This is 大脑 ，this is 小脑 ，OK？ 这个 now you get a sense 啊。In terms of computing, in terms of memory, in terms of information, right? How much information contained in natural language? How much information contained in motion control or muscle memory? 我们的小脑脊柱，对不对 ？Muscle 在做的事情。How much information in our visual memory? Okay, the world model. This is a world model. I mean, this is also part of the world model, right? Control, right? This is a part of model for perception. Inference, this is a part about execution, 对吧？执行，对吧？ Interact, 交互 right? This is also our physical model about our body and how we interact with the objects. Okay, so these two are consist of our world model. right? When you talk about it. All right. Any question so far before we still have a little bit of time to talk about maybe another application. Enough about 大佬, we can talk a little bit about 小佬, right? Any question? We may have a few minutes. Any questions so far? So that concludes. So today I just give. We don't have time to talk about all the application, but you'll see that probably chapter 7 will have more applications added in the future version, right? Some of our students are working on it. By the way, you can see that what I said today is a few work did by my current and the former students, right? Starting from Sindeno and also the MAE, or the white box, and also that even the recent RE is also this line of work, right? All based on now you understand the mental picture. You can do much better. You can not only understand what other people have done, or even understand things they don't even understand what they have done, okay? You actually can explain their heuristics, what they might be they're thinking, but they cannot even elucidate. They cannot even say out loud what they're really trying to do. You should be able to now, right? You can tell them this is what actually you want to do, right? Second, on top of that, because you understand what should be done, you can do better. At least you can do much simpler. You can simplify the objective. You can simplify the pipeline. You can simplify the architecture. You can unify them. You can explain them. You can even design better ones. Okay? You can working on different settings. You can work on the setting which is open loop. You can do in a setting which is better in open loop. You can do better in a closed loop, auto encoding. Also, you can do things they cannot do. You can do in a closed loop. Nobody has done that before. Okay? At least nobody has scaled it up before, right? So 我在现在 convince Peter, probably you guys, he should truly close the loop now, right? Right. So even we talk about transcription, we're still solving this end-to-end, right? We're still solving this globally. That's the mistake. That's a problem, right? It's hard to scale, right? You optimize encoder decoder all together end-to-end. That's actually, I'm sorry, globally, that's actually very expensive to do. That's why it's very hard to scale. But can we do this, right? Completely different architecture. Can we do this locally? Can we do this massively parallel? By the way, our brain doesn't have one loop, right? We talked about it before, right? We don't have one loop. We have multiple loops. So hence, we might be taking every cortical column, 我们的这个大脑皮层，对不对？我们是25万个并行的 unit， 所以 every unit might be taking a projection of this thing, learn its own information to do auto encoding for the fraction, a slice of the world. Okay, do the massive parallel. And then assemble them together. 明白吗？我们可能是几十万个 loop， 甚至还分很多 hierarchy， 而不是这么一个 loop。OK， RE 一个 loop 啊，不得了，对吧？我们又 scale up 了啊，我们又可以这么，还没开始呢，同学们，真的还没怎么开始呢，对不对？真正的 architecture, right? Truly scalable one, parallel one, right? Then also the associated optimization mechanism， 而不是闭着眼睛这几十一个参数一起给我 update， 对不对 ？backpropagate， 哇，全部给我求导，对不对？Nature does not have that option. Okay, we don't have that option. Right? There's much better options out there to do the same thing and do this much more efficiently. Right? To learn the distribution of this massive high-dimensional visual data or senses, and get the structure, get a highly organized, structured representation of that distribution, and be able to access it very efficiently when we need it for inference, okay? Instantly. we may not even able to afford to take that many iteration to access, okay? And this is on all the parameters, okay? You don't, right? When you detect a tiger in the forest, right? You don't have that many time, right? To do the inference, right? The reaction. So you can see our memory has to highly structured, right? So that it enable very efficient access, right? 绝对不能像这样，对吧？对吧？全搅在一起，对不对？啊啊，要 access 的还要去，对吧？So now you understand, right? In order to control, in order to access, the structure of the representation is highly important. Okay, actually, and has you have to make it explicit. All right, that's all. We have a few more minutes. I can talk a little bit about something else, right? So this is a time you can enjoy a lot of applications. We don't have too many lectures to talk about applications. There's a few more in the chapter 7, and we'll probably add a few more. And so we talk about the last maybe 20 minutes chat about this application. So as I said, those slides today, actually, I have to give credits. As I said, the early on, actually, we have to thank my students at Berkeley and also some others. They actually helped with over the weekend. Actually, many of them didn't even sleep for a couple of days. Ju Pai and help with the MAE, and Ziyang is helping with Seleno. Even Peter was helping with RAE, right? All these folks are really some of the latest work. We should be very thankful. And also that so the last piece I want to talk a little bit about Xiaolao, right? What our motion capturing, right? Motion, how do we estimate the human motion body? And there's a lot of embodied AI people, right? Everybody trying to do embodied AI, try to control robot, dancing, running, right? But the question is, how do we capture the motion, right? So there's a lot of jobs about try to talks about how do we this is the one. Do I want to use the full one? I don't know. This one is a bit longer, right? Let me try this one. I never seen. He sent me the full one, so I have the shorter one. But so this is basically the idea, right? So we have a lot of for right now robots. We want the robot to emulate human motion, right? But where that motion come from, right? You do 摇操, right? Some person wear some weird sensor suit, right? Or the Hollywood have all the actor put on a lot of motion capture devices. It's cost hundreds of billions of dollars, right? With magnetic sensors strap on your body, shoulder, or you have some some devices you human remotely control robots to achieve grab this. Hence you learn, right? Human control the robots to 炒菜，比如斯坦福那边瞎搞，对吧？对吧？就是拿些夹子，对吧？开始弄那个炒菜啊，然后呢，你 actually you don't know how painful it is, okay? Actually, how much work gone before the robots can learn how to achieve some of the things because someone has to remotely control those machine to achieve those tasks first. Then the machine gets to memorize what they did, okay? For the whole sequence of motion, right? Called imitation learning, so on. The question is so basically where the motion come from. So our memory, so our Xiaolao memorize a lot of things, right? We know, for example, I don't have anything. I know how to move my hands very naturally, okay? I don't do something very weird, okay? So we naturally know how to walk, how to dance, how to run, right? So the question is, where does motion come from? One scenario is that how do you capture this motion in a very natural setting， 对吧？而不用在这个摇操，或者是穿着这个 motion capture suit， 对不对？而且 as soon as you wear those, it become very unnatural, right? 我们 behave very badly. How the question is, how do we capture our daily life, our daily motion in a very uncontrolled, very natural setting, right? One of the ideas come up with that by one of my students is that bring is can we just use the goggle， 就是用的那个 Ariel 那个 Meta 的那个眼镜啊，就是这个眼镜可 provide the glasses providing two things for us. One is just the location of your head， 还有一个这个 IMU 啊，就是 inertial navigation sensor。Give you the head of the motion of your head. Second is it has a stereo camera, right? Has a camera, record the video. That's about it. 我们的就是 ego sensed, right? It's called ego video， 就是对吧？第一视角啊，对，就 egocentric 的 view. That's it. So the question is, can you capture the motion? Can you estimate your body motion from these two input? It's kind of interesting, right? 你看 you don't even see the rest of your body. 你看我们走路，我们也不知道我们的 body rest of the body 在干嘛，对不对？你是看不见的，对吧？我们一般在动的时候 we don't look at our body, right? We don't do this, right? We cannot see our body, but we're actually performing. But we probably only know where our heads are, right? The question is, just from the motion of your head, are you able to recover the rest of motion? And also, sometimes you see your hands, right? You see part of your arms. That's about it. Can you actually infer the rest of your motion, right? So this is actually the idea. So devise slam pose and ego motion, or put the body pose, height, hands in the allocation-centric frame, environment. Can we actually do that, right? So we wanted to take the input, take the head motion, and be able to capture how I'm moving around in the environment. So if I'm able to capture this motion, then I can ask robots to emulate, 对不对？去模仿。才能去模仿学习，对吧 ？Learn how to achieve those tasks, how to operate a printer, coffee machine, right? Play piano, play with PC, computers, and so on, cell phones, right? So this is actually basically the point. This is the question, right? How do we get from egocentric sensing to get the allocentric human motion, right? So input is pose. So the idea is very simple, right? Again, you can capture, there's a lot of data about the human motion, human body motion, maybe hand motion as well. Some of my students are working on it, right? Suppose you already had a lot of human motion data. You can learn remember, once you have those data, we can learn its distribution. Basically, the sequence of human motion, how people typically move, right? Let's say we can learn the distribution. You can learn. Maybe you can fix the length, right? 64针，128针，对不对？我的身体啊，各个关节 the links of every of my body, how they moves in the sequence. I can learn that distribution in time, how my body moves in time, right? You get hundreds of hours of human body motion. You learn those distribution. Then you condition on your head position, 对吧？这就是 perfectly 这个问题啊。是不是 ？First, I learn the distribution of x, right? Right. Using a diffusion model, right? I can access this distribution. So every point here representing 64针 natural motion, how human normally move. This is maybe dancing. This is maybe running. This is maybe walking. Okay. A sequence, right? That's a distribution. It's low dimensional. It's correlated. All the joints, all the motion are. It's not random. Okay. Our joints does not throw in the angles in a random way. Okay. Right. So we learn that structure. Now, when I only see the head motion, right? I don't see the rest of my body. I don't see the entire X, right? This is X. I only see a very tiny piece of X, which is my head, where a head is, right? Can I recover this? May not be uniquely, but this will restrict what is the motion should be, okay? 记住啊，这个解未必是唯一的，对不对？满足这两组方程的未必是唯一的。Maybe there is one-dimensional, two-dimensional solution. Doesn't matter. The sampling will allows me to sample those, right? I can generate those all feasible solutions, agree with the measurements, agree with the distribution. That's it. That's all you want. Right. So you can condition on the, where's my mouse? Why my mouse is gone? I don't know where. Anyway, or is, oh, this one. I don't know where. Yeah. So you can actually do, right? So this is you learn diffusion. I don't want to explain this. This is you guys should know how to do it, at least in principle. Okay, learn diffusion model and then condition on this, and also you should know how to do in principle. At least, right? Remember the diffusion posterior sampling we talked about last time, right? Doing the Bayesian inference based on this condition, and this is a prior, right? And you can actually generating the pose, right? Condition on the head pose, generating the rest of the body, or the rest was walking, dancing, or whatever, right? So here is the output, right? For example, the left is input, right-hand side is the output, right? Is the body that sort of you generated from the sample, condition on the head pose motion, right? You can see, right? So the rest of the body is actually completely regenerated just from the head pose, right? Right. Now, but what is the ground truth? Ground truth is on the left. It's a red one, right? You can see they are not exactly the coincide, but both are very natural. Okay. Right. Even the one regenerated actually agree with the head pose for sure. Second, is actually the rest of the body is actually quite natural. 就很正常，对不对？很自然啊 ，motion 啊 ，that you want. And also you can do more. As I said, that the solution may not be right. And also if you have the hand, right? If you have hand additional constraint, right? 有时候有人看到你的手在哪儿，对不对？你的手就决定你的 arm 在哪儿， the arm 就决定你的 shoulder 可能在哪儿。They give you more constraints on the rest of the body, right? Then you can probably do more, right? So for example, once you see your hand, then the rest of your body, arms also gets determined. Probably even your feet, you have additional information to decide the location and your pose, right? Right. So I'll skip this, right? This is let me go to the shorter one. The shorter one is actually probably, then if you want more technical, right? So now, remember the generation, the sampling is not unique. As long as anything agree with my observation, agree with the distribution, right? I can sample it. This is one solution. This is all possible solutions, right? Many possible solutions. All agree with the body, the head motion, right? 你的 hand 手在哪里啊 So this is actually come from the sampling, right? So maybe there's not just a unique solution satisfy those two things. There may be multiple. There's a variability in the data, right? Can generate. You can also do there's some other additional. Then once you are able to do this, oh, you see this is input, right? Your head motion and also this is what you saw, right? So you'll be able to actually see that how your rest of the body might be moving, right? 你看这个 sequence 你是从来没见到自己手的啊 ，you don't see the rest of your body at all, right? But you have to be able to recover what the motion, most likely motion, is actually doing. And with the hand, you can do this. Right, you can see your hand actually can probably infer, but of course this work has to rely on the hand detector is good, right? Some of my students still work on it, try to make this perfect or better, right? Also the hand motion, this relies on getting the hand estimated, right? Also you can do the same for the hand. If you have a diffusion model for the hand, if you see the hand from certain occulted pose, you can actually refer the rest, okay? In this work, we didn't do that. We just use whatever existing hand detector to do that, right? So you can actually further improve the estimation of the hand gesture if you have the distribution of the hand. You have a lot of data about the hand, how hand moves, right? You can do running and so on. It's kind of interesting. Right? Play piano, right? Can recover how the gesture in 3D, right? Playing, or this is, I think, I don't know, cell phone or a credit card. This is actually cabinets, open stuff, right? But this is definitely not everything, right? This is just motion. But in fact, if you see what this person is doing most of the time, what's missing except this sequence, right? Most of the time, our hands are manipulating something, 对不对? We're interacting with the object. That's missing. We only have the motion. But you can think about it in the future, what kind of motion, what information you want to capture. You want to capture how the hand interacting with object. Okay? You want to get a 3D shape of the object as well. Right? Then that is important. Yeah. 所以啊，同学们，你看这 embodied AI 还路还长，对不对？ It's a long way, right? Just to be able to do some action, dancing. That's the easy part, right? The harder part is that how we interact with the object, right? The visual part and the physical interaction part, that's still missing, right? Yes, we worked on the vision part. Remember, all the example I mentioned about the DIT, RAE, MAE are still just the stupid 2D images, right? We have not started with 3D objects yet. What about the 3D distribution? 3D objects, right? There's some work, people. 现在李飞飞在忽悠什么空间智能，对不对？ Has something to do with that, right? See, Fifi has been working on 2D image for 20 years, all her life, until recent years. Why he started thinking about the 空间智能, right? Because he's trying to apply vision. Before they thought the vision may be good enough for robots. He's trying to work for robots, but realizing all this generative AI, vision, image understanding and generative AI for images really works not at all for robots. Okay? 还差得远啊！所以如果你 just wish 一个 VLA 就能够解决 robotics，forget about it， 就是不要痴人做梦，好吧？对吧？想都不要想啊！这个好好的把3D 视觉解决好啊，好好的 solve the 3D problem。OK， 哎啊，弄个 language model， 加一个 multi model， 再加上 action VLA， 绝对就可以解决 embodied AI 啊！这些都是不知道是哪里来的这种，对吧？啊，痴人说梦的东西啊，连概念都没有对啊。 对，还早啊，所以现在还有很多东西要做。Right, so this give you the. If you want to know more, all right, this is actually additional work. If you're interested, there's actually the methodology how to do the conditioning right. In this case, it's actually not that trivial. Okay, although see 这堂课 although I taught you how to do conditioning inference in principle, that's a concept picture. But how to compute those things? How to enforce those conditions for each different data might require special treatment. Okay, require some customization 啊，对，你要去把这些条件怎么把它 enforce 好啊，在你的 sample 的时候啊 ，it's not that easy so you need extra some engineering how to do this per frame, especially you're dealing one chunk of the time, right? Especially you can only learn the distribution at the let's say 64帧，你还要把前后的接上啊？怎么接啊 ？Well, those are yes, indeed. See, even you learned the concept, even you learned the principle, to connect theory to practice, yes, there's still fair amount of engineering to be done and to be done correctly. 明白吗？不是说你懂了理论就 engineering 就不需要了，也还是需要的，知道吗？但只是。理论也好，原理也好，会让你少走很多的弯路啊，而且知道大概的正确的事情是什么，但是并不能省掉你所有的细节的实现啊。When you're dealing with images, when you're dealing with motion, when you're dealing with different type of data, And also when you're dealing with different types of conditioning, right? Even in chapter 6, right, we talk about different settings, even how the data were given to you, how the information given to you will decide the algorithm details different. Even conceptually, you are solving the same problem, okay? But depends on the condition, right? Condition of the data, condition of the format, and so on, right? And how you decide what distribution you are learning, right? How do we smooth patch them together? Oh, needs a little bit careful. Still needs a very good engineering to get them implemented correctly. So it's just like so actually, for example, here you have to handle how to deal with those transformations. There's multiple link rigid body, and how do you refer the ego? There is a representation. How do you represent your motion in an egocentric manner? How do you recover that motion in the allocentric？ 就是世界坐标啊，对吧？你的个体的 field-centric coordinate 啊，物体坐标等等啊，如何把它转换的正确啊 ？There's actually a lot of work to do, right? Also, how to enforce some environments. Anyway, there's details. I don't want to. Yeah, this is more demo, I believe. Yeah, you actually can sample different body shape, right? Now you actually have a lot of fun, right? So you have those distributions. You can actually, even same motion, you can actually generate in different motions that are consistent with the head positions. I have a lot of fun. Yeah. Yeah. Yeah, there's more actions. Yeah, this is actually about the land chill. Actually, it's still, it doesn't work all the time. There's still failure cases, right? There's still a lot of room for improve, both the accuracy, both the stability, and also how to work the body and hand again, right? Some of my students are also working on it. You get to learn a better distribution model. The more data, the merrier. Then if you get the distribution learned better, the F gets learned better, you're fine. And also hands, right? You don't rely on just a hand detector. Some other people did the work for you, but you wanted to improve that. Again, hands also self-occlude itself, right? There's a lot of also skill ambiguity, and also where the wrist is. How, if you want to attach the hand to your body, you have to know where the wrist is, right? And so on. How do you link the hand with your body and so on? There's actually a lot of work to do, right? So, but this gives you an idea, right, from this class. In general, if you have data, the data has good structure. How do we learn, right? From the data, the distribution of the data, and then hopefully learn very good. Now, but you saw the motion. Then what is the structure then? I want the last couple of minutes ask you a question. What is the structure? Yes, there's a low dimensional structure, right? It's a manifold of motion. We can sample, right? Sample. Then what is how our brain? Just imagine how our brain should organize the motion, right? For example, right? Right. How our brain organizes motion? We can sample. We can get this. This is the visualizing, but this is not control yet. We don't want to. We do not just want to generate emotion for the sake of to look. 所以现在包括李飞飞在忽悠的空间智能是完全是错的。OK， We don't want to recreate 3D model to look at it. 明白吗 We want to reason. We want to understand it. We want to interact with it. 明白吗 Be able to recreate 3D is not the purpose. Be able to regenerate the motion is not the purpose. We want to memorize things in a very modular fashion. 所以我要做这几个动作的时候，我该怎么把它结合起来？炒菜、跳舞，对不对 ？Swimming, sports, acrobats. How do we assemble a piece of furniture? sequence. So our memory of motion is also highly modular. If I see you, something I don't know how to do, you show me how to operate something, then I memorize. I can recall my memory, right? Recognize sequence of action. I can reassemble my motion, be able to do it. Right? So our memory is not just to generate some sequence that looks natural, okay? So our motion memory, our shallow, has to be also in somehow very structured motion, highly modular. 走路怎么走，对吧？怎么平衡？跑步怎么走？跳舞怎么跳？对不对？手该怎么做？Those are highly modular objects. Just like our visual memory, right? We recognize objects. We don't just get a whole bunch of point clouds or texture or mesh or splatter, right? Or lerf to look at. That's not the purpose at all. Our purpose is to actually be able to reason with every single object in the room. So I can count how many people. I know what's on you. I can tell you what's on your left-hand side, what's the right-hand side. I can switch from egocentric to object-centric to allocentric. 这个房间的中间，后面。Right? We'll be able to really have the understanding of object level views, the geometry, and so on. Right? Not just have the 3D reconstruction to look at it. Right? 就跟前面那个例子一样啊。We don't want to just have the environment, right? This is a 3D reconstruction, by the way, right? Reconstruct all the pixels. It's a crappy job, but actually you get a point, right? Something you can look. At least looks okay, okay? We don't want to just have the 空间智能 is not about just recover something to look at, okay? It's about something you can reason, you understand, right? You understand at object level. That's something you can interact, you can manipulate, okay? We have a long way to go, right? 所以不要被这些词汇有些这个炒作的这个忽悠，对吧？有时候真正搞清楚你要什么，所以很简单 ，OK？ 你就不用那么被忽悠了看着好像挺好，对吧？我可以生成一些 3D 看着好像挺好，那机器就理解了吗？ Far from understand, okay? Has no idea what it's looking at, okay? The machine, right? So this is something I think you really, really want to know. And through this course, I hope that we understand, at least in terms of building memory, right? How to generate memory, learn the data distribution from data, and why we need a very good representation as a structured memory, and then how do we use the memory for inferences. That's everybody has been doing, right? So far, at least we can very safely say, right? All the AI so far are very much learning the distribution of the data and try to reproduce it in a Bayesian way, right? And we're doing that. What is the way of doing it? We're doing that through a lossy compression, right? And through compression and through linearization and so on. And so this is, and we are identifying the reason we can do that because the data, the internal structures are low dimensional. There's a lot of correlations in it, right? Data are not random, they're highly correlated. Any data that are worth learning has information to learn must be low dimensional. And the way that we learn it is through compression, right? Denoising is a form of compression, right? Linearization is a form of compression. Right? Special form of. Hence, even the operators. That's why they share a common deep, right? Denoising-like operators. That's it, right? So hope that's it. I hope that people start to realize that, so that don't try to say 现在这些 AI 就是什么都在做，什么都能做，对不对？炒作的悬浮这些。现在我觉得现在好一点现在我在发现 Twitter 上至少。那个很多的人现在理智多了包括 Elon Musk 对吧？现在 AI 在做什么？大家都可能用的，现在都开始用类似的 language 其实在做压缩，在利用数据的 correlation 来做一些 regeneration 而已所以了解一件事情的本质可以保证我们不要对吧？把本质搞清楚 可以保证我们不会被忽悠啊，同时呢，可以让我们在 practice 上做得更好啊，避免太多的浪费啊，避免太多的弯路啊，这是我希望大家能够充分意识到的。所以 hopefully if you learn very well from the course, I'm sure that you will be at a very 你们已经在一个比其他人起点高得多的起点了啊，而且也希望大家意识到啊，对吧？这里还是 a lot to learn 啊，不是说现在你们跑来对吧，就觉得现在大家能做的就是现在就能做的就是 everything you need to learn no right no actually there's a lot of things to learn actually also there's a lot of new things to discover to do much better right 所以这是今天 OK that's about it 我们还有下节课呢我看看啊，我们就讨论一下可能第8章。或者是对I want to do a little bit summary and also hopefully that we can talk a little bit about recap the whole course and discuss what the future, but doesn't matter about not only for we can carry some open questions, right? What other things about intelligence? Now we know a piece of intelligence, right? The memory part of it and what the future? What other open problems, right, for intelligence, the natural one or even the scientific one, right, is and beyond the current understanding, right? What we currently have done, right? Even about today, even about this level of intelligence, what are the things we have not done correctly? Maybe we want to recap a little bit, right? And then how can we go further, way beyond? What's the next level of intelligence we should try to understand, then try to be able to truly reproduce the intelligence, 而不只是模仿啊，不只是东施效颦，而是真正把这个机制，对不对啊？比如说真正的基于理解、基于推理。所以可以大家就讲，我们现在学到的所有的 AI，everything we talk about right now，the AI，the intelligence is inductive. We learn the memory, we do Bayes inference, right? This is called inductive intelligence. Honestly, we have not done deductive. Then what is deductive? What is the mechanism behind the deductive, right? That's what mathematics or science relies on. What is that mechanism? What is the principle behind it? What is the objective? Why we have that level of intelligence? What purpose it serves? I don't think anybody has any clue at this point, right? So anyway, next time we may spend some time. You can think about it if you have too much time and when 晚上睡不着觉的时候可以想一想啊，对吧？对，可以思考一下啊这种问题啊。Maybe next time we can have some discussion about it. Okay, see you.